Now we're going to look at the energy stored in a charged capacitor, as well as what happens when you put other materials in between the plates of a parallel plate capacitor. Those other materials are known as dielectrics, and they change the capacitance a bit. So if we're looking at the work it takes to charge a capacitor, we're going to start out by remembering that voltage is defined as the potential energy per unit charge. So the potential energy is QV, and the work done is going to equal the potential energy, the work done by an external force, so we don't have to worry about a negative sign here. Now, as we're charging the capacitor, the first bit of charge requires no work because there's no voltage on the capacitor. But as we add charge, the voltage goes up, and so we require more and more work. So to find the total work done, we need to sum the infinitesimal works at the different voltage values. And then we can also remember that since Q equals CV, then dQ is going to equal C dV. So if we make all of these substitutions in, then we end up with the integral of V dQ from 0 to Q. And then we can also again substitute in Q equals CV into V there, and so we get a 1 over C is equal to, work is equal to 1 over C times the integral of Q dQ, and that works out to be this expression here. We can go back and substitute in Q equals CV a number of ways so that we can rewrite our equation for the energy stored in a capacitor in terms of Q, C, or V, depending on what information we have. Granted, you could just grab one of these and solve for the other quantities using Q equals CV, but it's easier just to grab the one that works straight off the bat. So let's look at a quick example here. We want to know the electric energy stored in a capacitor at that capacitance and that voltage. So if we think back to that equation there, I want to know the energy stored, and which version of that equation is going to be most useful if I have C and V. I'm sure you wrote down that big long equation and all the options you had, and so you readily see that the best choice is 1/2 CV squared. So we can just plug right into that, 150 microfarads times 200 squared, and we get 3 joules of energy stored in that capacitor. Now if we want to know the power output, if it releases this much when it's discharged, so like this picture here is showing a camera flash, this big fat thing here is a capacitor, so it releases the energy pretty quickly. Well, the power is just the work, or we could call it change in energy over time. So we've got these 3 joules divided by 1 millisecond, which is 0.001 seconds. So that is 3,000 watts, which is quite a lot of power. You know, your air conditioner cooling your entire house might use about 3,000 watts. But with a capacitor, that's all released really quickly. So it's a high power rating, but for a short amount of time. So it's not that much energy overall. All right. Let's look at another example here. If we charge a capacitor to Q and then disconnect it from the battery, and then we pull the plates apart so that they're twice as far apart as they originally were, what happens to the energy stored in the capacitor when we do that? So if we think about our equation for the capacitance in terms of its physical characteristics, if I'm doubling D, then I'm dividing my capacitance by 2, so my final capacitance is going to be half of my initial capacitance. And if I'm going to plug into my energy equation to see what happens to the energy, I also need to know either Q or V. And the nice thing is that depending on the situation, one of those is always going to remain constant. If we disconnect the battery, so we just have this capacitor floating off in space here, it's going to have a certain charge on it, even if we pull it apart, so to speak. And that charge has nowhere to go, so Q has to be constant. So that's nice, because then we can just say, well, the initial energy was 1/2 Q squared over the initial capacitance, and we chose this version because we know Q is constant, and we're also dealing with how the capacitance changes. So that's my initial energy. My final energy is going to be 1/2 the same Q, because I just talked about why it's constant. And now we have C, which is equal to 1/2 of the initial energy. So that just gives us this expression here, because that 1/2, if I'm dividing, well, I'll go ahead and show you. So I've got a 1/2 here, and then dividing that by 1/2, this 2 will end up in the numerator, and they'll cancel out. And so if we, just rewriting this again, compared to the initial energy, we now have twice as much. So equals 2 times the initial energy by doing that. Well, where did this energy come from? It came from the fact that you had to do work. You had to exert a force on this over some distance to pull it apart, and some of that energy that you exerted went into storing more energy in the capacitor just by pulling it apart. So let's look a bit more at that idea of disconnecting a battery and then changing the separation distance. In this case, we're going to decrease the distance. So what should happen there, if you look at the energy over here, if we decrease the distance, energy goes down, increase the distance, it goes up. And you'll notice the number of charges on here remains the same, so Q is constant. The voltage is not constant. Over here we've got a voltmeter. So if it was originally at 1.5, that was the battery voltage, and then we move it up and down, we can change that voltage. Now, it's a different story if it remains connected to the battery. In this case, V is constant because the battery is able to accept or provide additional charge in order to keep V constant, because you're connected to this equipotential surface here now. So again, the energy stored changes, but in this case it's because V is changing, not because Q is changing. Okay? Sorry, I got that backwards. It's because Q is changing, not because V is changing. And you see that you get more charges on there. So the important thing to remember when you're looking at things like this is if you're connected to the battery, that's not an N, connected to the battery, then V is constant, and Q can change. If you're disconnected, then Q is constant, and V can change. And that's an important bit of information that you should commit to memory. Okay. Now, we often look at what is called the energy density in that region of space between the plates of the capacitor, how much energy per unit volume is stored in there. And we can start out by looking at 1/2 CV squared. And if we substitute in for C the expression for the capacitance in terms of the physical characteristics, so A over D, hopefully we're starting to get familiar with these equations. And if we substitute in for V, E times D, because we have a constant electric field, and so V equals ED whenever you have a constant electric field. Now this guy's squared, so this works out to be 1/2 epsilon naught A, and the D actually cancels out with one of those D's, and we're left with the other D, and then we've got an E squared in here. Now this quantity, the area of the plate times the distance between the plates, that equals the volume between the plates. So I'm going to write it with my electric field squared here first, times the volume. And then what we often do is we divide the whole equation by volume, so we get potential energy per unit volume, and we write that with a lowercase u as opposed to a capital Q, which is the total potential energy. So this is the energy density, and it just works out to be 1/2 epsilon naught E squared, which this is an important conceptual expression here, that we can see that the energy density in any region of space is going to be proportional to the electric field squared, and we'll talk about that more later on in the course. On to dielectrics. If we insert some other material inside the capacitor, essentially we no longer have air in the gap, and so we are going to multiply our capacitance by some value K, where K is known as the dielectric constant. So for vacuum it's equal to 1, and so that just reduces to our original equation that we've been using. For air it's slightly greater than 1, small enough that you could probably ignore it, but for other materials it's significantly larger than 1, and it can increase your capacitance quite a lot. And whether you like to write the equation out like this one right here with K and epsilon naught, or you can just redefine epsilon, rather than having the permittivity of free space, we'll just say, well, we've got the permittivity of whatever material it is, which is equal to K times the permittivity of free space. And so you can rewrite your equation as epsilon A over D rather than epsilon naught A over D. And then sometimes epsilon is equal to epsilon naught if K is equal to 1, and sometimes it's not. All right. Jumping back to our wonderful little applet here. So if we go ahead and show the capacitance here, as I insert this dielectric, some random material with a K value of 5, as I insert this, my capacitance goes up. I have to zoom out so we can see this change. And as I take it out, it goes down. Now you'll notice we have the same thing that we discussed before. This is going to change the capacitance. So if the capacitance changes, either Q or V is going to have to change as well. And which one of those changes depends on whether the battery is connected or not. And the rule is exactly the same as before. If the battery is connected, that's going to hold the voltage constant, which means Q is going to change as C changes. If the battery is disconnected, Q is going to be constant and V is going to change, which you can see over here on my voltmeter that it does. Okay? Either way, the capacitance goes up when you insert the dielectric, and the capacitance goes down when you take it out. Let's work through one more example dealing with all of these quantities. So let's write down everything we're given here. We're given K is 3.4, voltage is 100 volts, D is 0.004 meters, and A is 4 meters squared. And we want to find quite a few different things here. We want to find C, we want to find the electric field strength, and we want to find the energy stored in the capacitor. So if we start out finding, do we also want to find Q? Yeah, also Q. Alright. Let's start out finding the capacitance. So that is going to be K epsilon naught A over D. And we know all of these quantities. K gives us 3.4, epsilon naught is still 8.85 times 10 to the negative 12th. A is 4 and D is 0.004, so we plug all of that in and we get 3.0 times 10 to the negative 8th as the capacitance. Okay, then we can use that to solve for Q, because Q equals CV. We now have the capacitance, 3 times 10 to the negative 8th. And then we just multiply that by our voltage, which was given, so 100. Don't even need a calculator for this one. 3 times 10 to the negative 6 coulombs. And we're almost there. If we want to find the E field next, going a little out of order of my list over there. Since we're dealing with capacitors, we want to use V equals ED, or E equals V over D. So that's just 100 over 0.004, which is going to give us 25,000 volts per meter. And since we know Q, V, and C, we could choose a variety of different equations to find the energy, but we'll go ahead and use 1/2 times Q times V. And that is going to give us 3 times 10 to the negative 6th times 100, which gives us 1.5 times 10 to the negative 4th joules of energy stored in our capacitor. So quite a few things to calculate, but the equations are pretty simple and pretty straightforward if you can remember when to use V equals ED and all these things. Alright, now if we remove the dielectric, so this is going to change the capacitance. We're not changing the plate separation. That's the only thing we change, is removing the dielectric, so no more dielectric. Now we want to find the new values For C, we want to find the new electric field strength, we want to find the new voltage, and we want to find the energy stored. So just by virtue of the fact that they didn't ask for the new charge, that might be a hint to you that the charge is the same. So Q equals 3 times 10 to the negative 6th, because here we're not talking about having any battery hooked up, and if no battery is hooked up, voltage changes and charge remains the same. So we can go ahead and find our capacitance is going to be just epsilon naught A over D. I guess we could just divide our other one by 3.4, but everybody likes writing out epsilon naught, right? Okay, so 4.004. This guy works out to be 8.85 times 10 to the negative 9th farads. Okay, so our capacitance went down when we removed the dielectric. Now I'm going to find my new voltage using V equals Q over C. Q, I said, is 3 times 10 to the negative 6th. C, we just found 8.85 times 10 to the negative 9th. And that is going to give us 340 volts. Then we can find our new electric field using V over D. 340 over 0.004, which gives us 85,000. So our electric field actually increases when we remove the dielectric. And then the energy stored, we'll go ahead and use 1/2 Q times V again. So 1/2 times 3 times 10 to the negative 6th times 340 volts. And turns out that our energy increases slightly, 10 to the negative 4th joules, for the same reason that we saw earlier when we separated the plates. It takes work to pull that dielectric out, and some of the energy of that work goes into changing the amount of energy stored in the electric field.